Okay, here's one of the applications that are linked to your SketchUp programs or AutoCAD. So when you create a building inside AutoCAD or a wall, how does it calculate the area? What it does is it takes the vector that you've created and applies our dot and cross product to calculating area. And this is how it works. So here I have any rectangular shape. So this is a parallelogram. All right, it's a parallelogram. The formula works, though, for a rectangle. This is kind of what we call the worst case scenario. For those that forget, area of a parallelogram is base times height. And because it's a scalar, we want the magnitude. Okay? Area is a scalar. You never say, yeah, it was 20 square meters to the left. So it doesn't make any sense. So there we go. So we're looking at a scalar value. So the base. Well, I've got the vectors labeled as B, W, and H. So the base here is the vector B. So we want to know the magnitude of vector B. The height right here is the height of the y component for the W vector. So if we have some angle theta in here, how do you find that projection, or that the y component for that W vector? It's from our formula when we're converting vectors to algebra form, magnitude of the vector, and in this case it'd be sine theta. And we're looking for magnitude, so those outside bars mean it's going to be absolute value. And it's if it's a vector inside, we've got to find the magnitude. Where have we seen this before? Magnitude of a vector multiplied by the sine of the angle. If you look back in your note, you'll find that it's simply the magnitude of the cross product of two vectors. So if you define a wall in SketchUp and say this is the direction, so it records the x, y, z component for your wall, and it stores it as a vector. Same thing with the width or height, and then you say calculate the area of the wall. This is what SketchUp or AutoCAD is doing. It's taking the vectors that define your wall, and they're doing the cross product to get the resulting area. So there you go, a piece of programming software background for you. On to the next one. So what happens if we're dealing with the volume? So now this is the volume of a parallelepiped, which is any rectangular prism. So this one's just parallelogram, 3D parallelogram, so we can call it a parallelepiped. It could be also just a regular rectangular box. Okay, so same process here. We're going to label our vectors. So let's call this again vector B for the base, A, and then we'll give it some depth. So let's go, it doesn't really matter what we call it. And then we're going to have a height. Okay, so looking at the base, the floor of this parallelogram or parallelepiped, it's just a parallelogram. So I'm just going to go back here for a second. Volume is base times length times height. Again, it's a scalar. It's a volume. So I'm going to put those absolute value bars showing that we're looking at the magnitude. We already know that the base, we know the formula for base. Okay, so I'm going to break it into base times length. Base times length multiplied by, multiplied by height. So I'm just breaking it apart here. Maybe we'll do brackets. Maybe that's the best to do here. So base times height multiplied by base times width. There we go. Now I'm on board. And we know base times width, that's just the area of a parallelogram. So from the previous page or the previous part of the note, we know that that's the magnitude of B cross C. Now we got to transform this H value into a vector notation because we don't know the height per se. So what we do then is we know that height, and I'll just put the interior part in here. We know height, or the H vector, is the y component for my A vector. So it would be the magnitude of A sine theta. And then from there, actually, my mistake here, I want to use a projection here. instead of the y component. So if I'm looking at the projection, we're looking for the projection of A onto, and what I want to do, H is really where I want to go, the projection of A onto H, which is the y component, but this is also equal to A onto the H vector is perpendicular to the base, which means that if we were to take the cross product of B and C, then it would give us our H vector. So we want to find the projection of A onto B cross C, and using the formula we talked about earlier, the resulting formula with that is our A dot B cross C over our magnitude of B cross C. So this is just from our work on projections on the first part of this slide. Okay, so substituting that in. So we use that to substitute into the formula. So that means we're going to have, and we'll leave this in brackets, and then in brackets here, we'll do A vector dot B cross C divided by the magnitude of B cross C, and it's all a magnitude. Now we have some simplification because in the numerator we have the magnitude of B cross C, in the denominator magnitude of B cross C, so those will end up canceling out. So in the end, the volume of any 3D shape is the magnitude of B cross C dot, using the dot product A, okay, which is also, and we'll just put that note underneath, so there is your volume of a 3D parallelepiped. Also the formula for 3-space. So it's our check for 3-space as well. Okay, so if it ended up that the 3 vectors, A, B, and C, were on the same plane, coplanar, you'd end up with a volume of 0. Well, this formula then makes sense because that would mean that you don't actually have a 3D shape, you have a 2D shape. All right, so that formula also calculates the volume of a 3D parallelepiped. All right, now, I already talked about these, so I'm not going to go into detail. So work, this is from physics, work is force dot your displacement d, and we know it as u dot v, and we also know it as the magnitude of u, magnitude of v, cos theta. I'm not going to go through because that's how I developed the dot product, was using work. Similarly with torque, torque's a vector. It's applied force crossed with your lever arm. We know it as u cross v, and we also know it as the magnitude of u, magnitude of u, magnitude of v, sine theta. Magnitude of v, sine theta with the direction hat. Okay, so there are your formulas. Work is measured in capital J, so that's joules. And torque is Newton meters, and for the people who have done some work in the shops, also pound feet for the imperial conversion, so Newton meters. Those are units here, Newton meters. And now we have some examples. That's all. We've got the theory done, showing you a couple of applications. So, if u vector and v vector are as such, find the projection of u onto v and the magnitude of the projection. So, at this point, just straight formula. So projection u onto v. So we're basically looking for what kind of shadow does u cast on the v vector, and we know the formula to be u dot v multiplied by the vector v over the magnitude of vector v squared. So off to the side here, I'm going to do some side calculations. I'm going to calculate u dot v off to the side. You can do it all in the formula. It's whichever you're more comfortable with. And -2, 1, -3. So that gives me 2 plus 3 minus 18. So that gives me a 5. So -13 is u dot v. My magnitude of v, excuse me, would be the -2 squared plus 1 squared plus -3 squared. So the x, y, z components. So that's, let's see, 9, 10, 14, square root of 14 units. Excuse me. So returning over here, u dot v is -13. The v vector is -2, 1, -3. -3 divided by root 14 squared, and cleaning that up, it'll be -13 over 14, because the square root and the square undo each other, inverse operation. And as I said before, when you did unit vectors, don't distribute it in. Same thing here. Don't distribute the -13 over 14 in. It's really, the book does it with their answers, but I'm more interested in the process, so it's a extra step that's not really required, in my opinion here. Magnitude then. So magnitude of the projection. So that formula as well, we have that from the earlier one, and that is the magnitude of u dot v over magnitude of v. U dot v. And in this case, the top horizontal bars here, or vertical bars, sorry, they are actually serving as absolute value, because when you're talking about a magnitude, you never refer to it as a negative distance. So it means your result's always going to be positive. So how long is this vector, or this projection? It's going to be 13 over root 14 units. You never say -3 kilometers, or how tall are you, -6 meters. It doesn't work that way. Always in positive, so that's why it's absolute value. All right, so there is your answer to this particular question, or this particular example. And I will finish this up hopefully in the next video.